Hello, this is Charlie, and welcome back to the last video for Chapter 1, and this video is all going to be about the atmosphere. So let's get started. First off, definition: air is a mixture of gases that behaves as if it's a single gas. Air is odorless, colorless, tasteless, and blended so thoroughly that it behaves as a single gas. So if we're studying the atmosphere, there's different ways that we can look at it. We could study it in terms of composition. There's two layers based on the gases, the composition of the atmosphere. Temperature, how hot is each part and why. If we're looking at it in terms of temperature and what is heating it, we can divide the atmosphere into four layers. And function, what have you done for me lately? In terms of function, we can look at two different layers of the atmosphere that behave differently in protecting us from harmful radiation from space. So function, I'm not talking about oxygen that allows us to breathe and exist. Function, I'm talking about our atmosphere acts as a filter and filters out really harmful, the shortwave radiation, ultraviolet X-rays, gamma rays get filtered by the atmosphere, and there's two layers that do that. So the top of the atmosphere is about 480 kilometers above Earth's surface. Beyond that is space. It's a vacuum. Scientists say that they can detect the atmosphere out 32,000 kilometers from Earth. But really, once you're up 480 kilometers, you're in space. You might as well be. So because Earth has mass exerts a gravitational attraction. Mass attracts mass. The larger, the more massive an object, the greater the gravitational attraction. So if Earth was larger, it would have greater gravitational attraction, and we could have a thicker atmosphere. At the other end would be the moon. The moon is so small, it doesn't weigh enough to actually generate enough gravitational attraction to keep an atmosphere. You might have known air pressure at sea level is highest because gravity is pulling everything towards the center of the Earth. And as gravity is pulling all the molecules in the atmosphere towards the center of the Earth, they are bunched together closest at the surface. And as they bounce off each other, they exert force, and that's what causes air pressure. Air pressure is caused by the molecules bouncing off each other. They're packed in the densest at the surface, so they bounce off each other the hardest at the surface. And we can measure that force, and it's approximately 1 kilogram per square centimeter or 14.7 pounds per square inch at sea level. So this is a profile of the atmosphere, and right now we're looking at two different ways. On this side we've got composition. What is it made of? From 80 kilometers up to 480 kilometers. There's really only a couple altitudes that you're going to need to memorize. 18 kilometers is one of them, 50 kilometers is one of them, 80 kilometers is one of them, and 480 kilometers. So from the surface to 80 kilometers is the homosphere, from 80 to 480 is the heterosphere. In the homosphere, from the surface up to 80 kilometers, which is about 50 miles, wind mixes the gases together so that if you took a sample any place in the homosphere, the ratio of nitrogen to oxygen to carbon dioxide would be the same. There would be fewer molecules per sample as you get away from the surface, and I'll talk about that in a minute, but the ratio of, like I said, oxygen to nitrogen to carbon dioxide would remain the same. Above 80 kilometers, that wind and mixing, like wind bouncing off of continents and mountains and buildings, mixes everything. But above 80 kilometers, there's nothing really to cause mixing. And so what happens is the layers separate out, kind of like if you have ever seen oil and water dressing, like Italian dressing made of oil and water. The oil floats to the top, the water sinks to the bottom. And that same thing happens with gases. So there's a slightly higher concentration of oxygen and nitrogen towards the bottom of the heterosphere. And there's a slightly higher concentration of hydrogen and helium at the top of the heterosphere. In fact, I just said that the atmosphere extends out to 480 kilometers. Well, the International Space Station actually flies around in the heterosphere. So in the space station, astronauts are weightless. They are far enough away from Earth that they're weightless. There's not enough air to breathe. They might as well be in space, but they're still inside Earth's measurable atmosphere. So in terms of composition, we have the two layers, the heterosphere and the homosphere. The homosphere, homo means same. It's mixed together, so it's all the same. Hetero means different, so it's separated out into different layers. In terms of temperature, we'll look at that in a minute. There's 4 layers, but on this side, I want to look at the pressure graph. So you can see at the surface, we have 1,013.2 millibars. You need to memorize that number. I'll say it again, 1,013.2 millibars. A millibar is 1,000th of a bar. So standard air pressure is about 1 bar, or 1,013.2 millibars is average sea level air pressure. As you go up, it exponentially decreases. So in the first layer, the troposphere, from the surface up to about 18 kilometers, about 90% of all of the molecules are in the troposphere. About 10% of the molecules are in the stratosphere, which goes from 18 up to 50 kilometers. And then once you're above the stratosphere, there's hardly anything there. So on this side is showing us the percentage of sea level pressure at sea level. It's 100% because it's the same. When you're at the top of the troposphere, it's 10%. By the time you're to the top of the stratosphere, it's 99.9% less air than at the surface. And at the top of the mesosphere, there's still less air. Here's a nice diagram showing the molecules are spaced out. The molecules are bunched together. In fact, if you were standing on top of Mount Everest, 2/3 of all the molecules in the atmosphere would be below you, 1/3 would be above you. And that's about the same when you're flying in a jet plane. When you're flying in a jet plane, 60, 70, 80% of the molecules in the atmosphere are below you. Even though you're only at like 30,000 feet. I mean, the top of Mount Everest is 29,000 feet or so. So air pressure decreases exponentially, very rapidly at first, and then it just drops off very slowly down to nothing over hundreds of kilometers. So composition, temperature. In terms of composition, the atmosphere is divided into the heterosphere and the homosphere. The homosphere is mixed together from the surface to 80 kilometers. There's slightly higher amounts of ozone, which is triatomic oxygen, from 19 to 50 kilometers, and I'll talk about the ozone layer separately. That's a functional layer, so that's a little preview. The heterosphere is layered by density. Between 80 and 480 kilometers is the heterosphere. Lighter gases aren't mixed. Almost none of the atmosphere is in the heterosphere. So this is the atmospheric composition of the homosphere. These are the numbers that you need to know. And the numbers that you need to know, you can round. 78% of the atmosphere is nitrogen. 78% of the almost 80%. So 78% of the atmosphere is nitrogen. 21% is oxygen. 1% is argon. And 0.40% is carbon dioxide. Barely anything at all. In fact, carbon dioxide levels are so low, it's measured in parts per million. So for every million molecules of gas in the homosphere, 410 of those million molecules are carbon dioxide. 780,000 would be nitrogen, 210,000 would be oxygen, 400 would be carbon dioxide. So carbon dioxide, very small part of the atmosphere, but incredibly important, because out of all these gases, carbon dioxide is the only one that absorbs and releases heat. It is the only greenhouse gas that we're looking at right now. So 0.04% of the atmosphere is carbon dioxide. If we had no carbon dioxide, life would be impossible. There would be no plants. But if we had no carbon dioxide, the average temperature of Earth would be about freezing. So a little bit of carbon dioxide has a huge effect on temperature on Earth. Okay, this is the Keeling curve. The Keeling curve is named after Charles Keeling. He was a researcher at Scripps Institute down in San Diego. In 1958, he started measuring carbon dioxide. I installed an instrument on top of Mauna Loa on the Big Island of Hawaii, away from cities and pollution. And it's the longest record of carbon dioxide that we have. So the blue line is a smooth average, and you can see back in 1960 we had like 320 parts per million, and now we're well over 400 parts per million. So the overall trend is every year more and more and more carbon dioxide as we burn more and more fossil fuels. So the overall trend from 1958 to the present is more and more and more, but within each year, there's a seasonal pattern. The highest CO2 values in the atmosphere for a year are found at the end of the winter, and then the lowest values are found at the end of the summer, which totally makes sense because during the summer, plants are absorbing carbon dioxide, making it into plants. In the wintertime, they don't do as much, so carbon dioxide is going to build up in the atmosphere, building up, building up. It's summertime, the plants go crazy absorbing carbon dioxide. Plants are kind of dormant, except that, as you know, because you've already tackled the seasons, when it's winter in the northern hemisphere, so the plants are all sleepy, it's summer in the southern hemisphere, so the plants down there should be going crazy and absorbing carbon dioxide, but they're not, right? Because if the southern hemisphere was taking over in the winter, over the course of a year, CO2 would just be a flat line. So let's look at this. This is NASA's Blue Marble. This is going to be an animation throughout the course of a year. And we're starting in winter. You can see it's winter in the northern hemisphere because there's lots of snow and ice. And now we're coming up to summer. So the plants are going crazy in the northern hemisphere all long days, right? Because at 60 degrees north in the summertime, you're having an 18-hour day. So the plants are going nuts in the summertime and absorbing carbon dioxide. Now it's wintertime. The plants in the northern hemisphere are mainly drop their leaves, right? The reason plants drop their leaves is because the ground freezes in the winter, so they can't get any water. They continue to lose water through their leaves if they had any. So if you see a tree and it drops its leaves in the winter, that tells you that tree evolved in a climate where the winters freeze solid. In California, we have a lot of trees that drop their leaves in the winter, but they're confused. In California, our dry period is the summer. The Mediterranean climates, California, the Mediterranean, parts of South America, parts of South Africa, parts of Australia are the only places that have Mediterranean climates, and Mediterranean climates are the only climates that have a drought in the summer. So our trees, if they're evolved in California, many of those trees will drop their leaves in the summer when it gets to be too dry. So trees in California should leaf out in spring when it starts, or rather they should drop their leaves in spring. In fall, they should leaf out because it's about to start raining. They should keep their leaves all winter, and then in spring, when the drought starts, trees in California should drop their leaves. So trees in California would drop their leaves 6 months out of phase with trees from the East Coast or higher latitudes where it's going to freeze over in the wintertime. Okay, so now we know why trees all over the world, but now we know why some trees drop their leaves in the winter, why they go dormant. But that doesn't answer the question of what's up with the southern-northern hemisphere mix. Well, here's the equator right in the middle of Africa. You can see most of the land is in the northern hemisphere, and in the southern hemisphere, this is like 60 degrees south. There's like nothing there. This is 60 degrees north. At 60 degrees north, you're going across Alaska, going across Scandinavia, all of Russia, for crying out loud, about 60 degrees. 60 degrees south, there's nothing there. So in the northern hemisphere, in fact, when we look at as it goes to summer, so it's going into spring and into summer, you can see in the southern hemisphere, like there's a little bit of snow here, but so the only place where you'd have deciduous trees is this little sliver of the tip of South America. So I hope you enjoy the video. I could watch that for hours, watching the snow melt and come back. It's Earth's breathing on a cycle of a year. And that explains why the pattern of CO2 goes up and down over the course of a year. So another aspect of carbon dioxide is there's never been humans. There have never been humans that have experienced carbon dioxide at the present level. In fact, yeah, this is pretty good. Carbon dioxide is above 400 parts per million. Over the last million years, carbon dioxide has never gone over 300 parts per million. It's gone up to like 280, down to 180. When it's 180, that's a glacial period. And you're looking at like 3,000 feet of ice over Chicago. Much of Canada, much of Scandinavia, much of England completely covered with ice. So we have these patterns within the last ice age, which started 2.5 million years ago. We've got this pattern of 10,000 years of warm, or rather, sorry, yeah, 10,000 years of warm, then 90,000 years of cold. Warm, cold, warm, cold, warm, cold, warm, cold, warm, cold, warm, cold, warm. We were beginning to slide back down with carbon dioxide, but then humans discovered that we could burn fossil fuels, and CO2 has gone from 280 parts per million to over 400. You will never see a day in your life with CO2 levels below 400 parts per million. That's just never going to happen, which is just terrifying. Because I said before, the difference between no carbon dioxide and 280 parts per million is a habitable Earth. The difference between 180 and 280 is 3,000 feet of ice over Chicago. So we're going from 280 way past 400, and we're not really slowing down. So the future is going to be hot, 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 hotter. Temperature. All right, we got 4 layers based on temperature. So I'm going to show you this, go through it, and we'll probably come back to this picture because I think that'd be best. So there's the troposphere from the surface up to about 18 kilometers. From 18 to 50 is the stratosphere. From 50 to 80 is the mesosphere. And from 80 to 480 is the thermosphere. So let's go through these. Starting at the top, we got the thermosphere. The top of each layer is the whatever that layer is, pause. So the top of the thermosphere is the thermopause. And in the thermosphere, there's super high temperature, but there's no heat. Heat is the flow of heat energy. So there actually aren't enough molecules for there to be molecules to transfer heat energy. So there's like a couple molecules there, and they're really excited. Temperature is a measurement of the kinetic energy of molecules. It's actually a measurement of their vibrational energy. The faster they're vibrating, the higher the temperature. At 0 Kelvin, which is absolute zero, there's no energy for anything. There is no movement. There is no nothing at absolute zero. So in the thermosphere, there's high temperature. The molecules that are there are very excited, but there aren't enough molecules to transfer energy. The mesosphere is the absolute most boring. From 50 to 80, there's hardly any gas. There's no weather. The only thing they have are these things called noctilucent clouds. They're ice crystals. They catch sunlight after the sun is set, and they have this kind of rippling, pearlescent. They're gorgeous, but they don't really do anything. They're just kind of cool. The stratosphere from 18 to 50 kilometers. It's also called the ozone layer. The stratosphere is what blocks ultraviolet light from frying us. This is a picture of Felix Baumgartner doing the Red Bull stratosphere jump. He was assisted by a guy named Captain Kittinger, and I've thrown a video of Captain Kittinger's jump. Captain Kittinger jumped back in the 1960s from a balloon that was about 100,000 feet above the surface of Earth, and I'll talk about that later. And then finally, the troposphere. The troposphere, I gotta say, it's my favorite layer. It's the most important layer. It's the layer that we live in. It goes from the surface to 8 to 18 kilometers. Over the poles, because it's colder, the air is more compact, so the top of the troposphere is lower. Over the tropics, the air is warmer, so it's expanded, so the top of the troposphere is 18 kilometers. You don't need to know the 8 to 18. 18 is good enough. From the surface to 18 kilometers is the troposphere. The troposphere is heated by the ground. So as you get away from the ground, the temperature decreases. Sunlight on the ground warms the ground warms the troposphere. So as you get away from the surface, it gets colder. 90% of all the molecules in the atmosphere are in the troposphere. All of the weather, almost all of the water vapor, all of the clouds, all of that happens in the troposphere. As you get away from the surface, it cools off at what we call the normal lapse rate. So every kilometer you get above the surface, the atmosphere gets colder by 6.4 degrees per kilometer, or 6.4 degrees per 1,000 meters. Okay, so let's go back to this. So in the troposphere, we've got, or rather looking at the atmosphere in terms of temperature, the surface temperature of Earth is about 15 Celsius. These are numbers that you're going to need to know. So the surface temperature is about 15, As you go up through the troposphere, it gets colder because the troposphere is heated by the surface, and it gets to a temperature of about negative 57 Celsius. That is, in fact, by definition, the top of the troposphere is wherever you get, as the temperature goes down, wherever you hit negative 57, that's where the top of the troposphere is. At the top of the troposphere is the stratosphere. The stratosphere is heated by ozone absorbing ultraviolet radiation. I'll talk about that when I talk about the stratosphere, but you can see in the stratosphere it's getting warmer. It's going from negative 57 up to 0 degrees. Nothing's happening in the mesosphere. It goes from 0 down to negative 90 because there's nothing heating it. There's hardly any gas there. There's these ice crystal clouds that just look pretty. And then we get into the thermosphere. The thermosphere is going from negative 90 up to about 1200 Celsius, which is over 2000 degrees Fahrenheit. However, like I said, there aren't enough molecules to conduct electricity. There aren't enough molecules to conduct temperature, to conduct heat. So there aren't enough molecules to share that heat energy, so there is no temperature. There's hardly anything up there at all. Troposphere gets colder as you get away from the surface because it's heated by the surface. The stratosphere warms because it's absorbing ultraviolet light and converting it to heat. Mesosphere gets colder. Thermosphere gets warmer because there's hardly any molecules, but those molecules are getting hit with raw energy from the sun. So enormous amounts of energy coming in from the sun. They're hitting these molecules. The molecules are getting really excited, but there's hardly any molecules there to get excited. It'd be like going to a party in a gymnasium, but there's like one excited person running around. And that's like the thermosphere. Okay. Functional layers. We got two. We got the ionosphere, which absorbs gamma rays and X-rays. The ionosphere is also the same as the heterosphere. So the general region of the heterosphere is also the ionosphere. The ozone layer absorbs ultraviolet light. The ionosphere occupies the same space as the thermosphere and the mesosphere. Those are two layers defined by temperature. The ionosphere absorbs cosmic rays, gamma rays, X-rays, short UV. The ozone layer is the stratosphere. Up there's this oxygen molecule made up of 3 atoms. These ozone molecules absorb ultraviolet radiation and convert it to heat. Energy is never created or destroyed, it's just transformed. So these molecules preferentially absorb ultraviolet radiation, and then they release that ultraviolet light as heat. So in the stratosphere, at the surface, there's these chemicals called chlorofluorocarbons, or CFCs. They get hit with ultraviolet radiation, which breaks off a chlorine. That chlorine migrates up into the stratosphere, and it busts up an ozone. So you end up with a chloroxide and 2 ozone molecules. That gets split up. The chlorine gets split up, and you end up with a chlorine and an O2. And then that chlorine goes and attacks another ozone, making a chloroxide and an O2. That chloroxide attacks another ozone molecule, breaks it apart, and you end up with a free chlorine and another O2. So every molecule of chlorine, every chlorine molecule, or atom rather, that gets up into the stratosphere can break apart 100,000 ozone molecules. So it used to be in the stratosphere, there's ultraviolet light breaking apart ozone, but now there's ultraviolet light breaking apart ozone, and also chlorofluorocarbons are also breaking apart ozone. So the sun breaks apart, bashes together, so we've got 2 things breaking and 1 thing fixing, when we used to have 1 thing breaking and fixing, so the total amount of ozone would stay the same, because the same ultraviolet light that's breaking apart the ozone into oxygen and then O2, O and O2 from ozone by the sun, that's also now being done with chemicals. So the sun is bashing it back together and breaking it apart, but now this other force has tipped the balance. And so ozone, for a long time, had been decreasing in the stratosphere. In fact, they put a monitoring device at the South Pole to measure how much UV light was coming in, or rather, how much ozone there was, the strength of the ozone column above it. And they told the instrument, hey, if the readings are this high, you're broken, and if they're this low, you're broken, so you don't need to transmit any data. And the unit sat there, didn't transmit data. They sent somebody out to look at it, and they realized, holy shit, it's not that it's broken, it's just that there's no ozone. And so because of that lack of ozone, more and more ultraviolet light is coming into Earth. We have had the Montreal Protocol was an international agreement to phase out the use of the chemicals that are destroying the ozone layer. That gives me hope for climate change, that once upon a time, the nations in the world got together and said there's a global environmental problem and we will fix this globally. So we just need to do that with climate change now. The difference is that the ozone-destroying lobby was making chemicals that we use in refrigerators, and they found other ones that they could make more money off of, so that's what we use now, that don't destroy the ozone layer as much. The problem with climate change is we've got to find something, well, we know what it is. There's all kinds of options instead of using oil for energy, but there's so much money to be made in oil, we're probably not going to ditch it until things are catastrophic. But the ozone layer, we think, is going to make a recovery. The ozone layer, and I'm going to bounce back for just a second. The ozone layer, I keep talking about air pressure and how rapidly air pressure decreases. So the stratosphere goes from 18 to 50 kilometers, so it's 32 kilometers thick, which seems pretty thick. But the air pressure there is very low. So if you imagine the stratosphere as like a big fluffy sponge, and the molecules in the troposphere are like as close together in the molecules as a piece of wood. Okay, so the molecules are all spread out, the molecules are close together. If you compress the stratosphere so the molecules are as close together as they are at the surface, the whole stratosphere would get squished down to the thickness of a dime. So if you took all the gas in the stratosphere and you brought it down to the surface, at normal surface air pressure, the whole stratosphere would only be as thick as a dime, and that's the only thing absorbing ultraviolet light from the sun. So the stratosphere, or rather the ozone layer within the stratosphere, is incredibly important to life on Earth. Okay, that takes care of temperature and function. Boom. Variable, that means it varies. The static or unmoving things, oxygen, nitrogen, carbon dioxide, or let me put those in order, nitrogen, oxygen, argon, carbon dioxide. So the variable atmospheric components are pollution. So gases, particulate matter, chemicals that are hazardous to humans. Some of them are natural. Wildfires, volcanoes are examples of variable atmospheric components. Wildfires, here's a satellite image, remote sensing, using passive sensors that's just visible light from August 20th of this year, showing the plumes of smoke stretching thousands of miles down to the south and then up into Oregon. So that would be an example of a variable atmospheric component. Volcanoes, this is Eyjafjallajökull in Iceland. It erupted just after some members of Congress said, we'd like to cut government waste, so this volcano monitoring program, we don't really need that. And then Eyjafjallajökull erupted and shut down air traffic in Europe for a couple weeks. Because if you fly, if you fly a jet airplane into one of these clouds, the ash from volcanoes is actually little itty-bitty microscopic bits of glass. It's not ash like paper. When you burn paper or wood, the ash is very soft and falls apart. The ash from volcanoes is incredibly hazardous to your lungs. And if you try to fly a jet engine, the ash actually melts onto the engine, and then the engine completely stops and your plane falls out of the sky. So it turns out volcano monitoring is really a pretty good thing to do. Another shot of California wildfires. In this case, we're above the wildfires. This is dust coming from the Sahara. In fact, within the last couple of years, our understanding of dust in the Sahara and going to the Amazon, our understanding of that has increased dramatically. I'll find news or video on that. It turns out that the Amazon is fertilized with dust from the Sahara in Africa. It travels thousands and thousands of miles across the Atlantic Ocean, lands, and fertilizes the Amazon. And the trippiest, my favorite part, you know that the Sahara is a desert, but the dust that's being blown are little microscopic skeletons left over from millions of years ago when the Sahara was underwater. So the dust that fertilizes the Amazon comes from one of the world's great deserts, but the dust is made up of the microorganisms that used to live in the ocean, that used to be there millions and millions of years ago when sea levels were different. A couple factors that affect air pollution: winds, landscapes, and temperature inversions. And in Sacramento, in the valley, we have all three of these. We get our wind from the Bay Area, usually. So it picks up pollution on its way. We get our air pre-polluted. We also have inversion layers. So I just went over the idea: as you go up through the troposphere, the temperature decreases. So in the troposphere, the warmest temperatures are at the bottom. And as you go up, it gets colder and colder and colder. So if you have pollution or smoke and it's warmer than the air around it, it'll rise like a hot air balloon. And as long as the pollution or smoke is warmer than the air around it, it'll keep rising. Well, sometimes that profile of just steadily getting colder gets messed up. In Sacramento, what happens is in the winter, we get cold air flowing off of the mountains and it pools in the valley. So you get this big pool of cold air, and the cold air lifts the warm air up. So in this case, the inversion layer is the warm air that used to be on the ground that got lifted up by the cold air that flowed off the mountains. This is Los Angeles. They get the same thing in Southern California, except there it's the sea breeze. So when it gets warm inland, it pulls in air off the ocean. The air is cool, and it lifts up the warm air. So then you have a layer of cool air, a layer of warm air, and on top you have a layer of cool air again. So the pollution rises through the cool air until it hits the inversion layer, which is then warmer than the pollution, and so the pollution just stalls out. It can't rise anymore because it's colder than this warm layer that's above it. Eventually, this is going to release heat and get colder, and everything will mix together and go away. But then the whole thing starts up first thing in the morning in Southern California. As soon as it gets warm, you get the sea breeze, you get an inversion layer, and here you can actually see the top of the inversion layer. There's some places in Southern California in San Bernardino County that back in the 1970s, the trees would be killed up to the bottom or the top of the inversion layer. So you can see the pollution that was killing trees. So on the hillside, you'd have a reverse snow line, that you'd have dead trees in the inversion layer and then healthy trees above it. And some more pictures of inversion layers. This is in Scotland. You can see the warm air rising, hitting the warmer air, and it can't move any farther. And then it just moves sideways, and it's trapped like a lid. I often use that term. It traps it like a lid. And sometimes it really looks like it. This is Salt Lake City. Salt Lake City, again, it's in a basin. So there's all these mountains. The cold air flows off the mountains, and then it lifts up the warm air that was on the ground, and you get this nasty inversion layer. So we get inversion layers in Sacramento. In fact, if you ski or go up to Tahoe or any place up in the Sierras, you can drive up on 80 and it'll be cloudy and foggy, especially in January in Sacramento. It'll be foggy in the valley, and as you're driving up 80, eventually you pop out above it and it's warm and sunny. And you look back at the valley and it's socked in with this thick layer of fog. And what you're actually looking at, you are in the inversion layer. You're looking at the cold air back down in the valley. So enjoy that next time you see that. You can think, oh, I'm in the inversion layer where the air quality is better. Look at all those poor bastards in Sacramento breathing that nasty air that's trapped by the inversion layer. So anthropogenic pollution. Anthro means human. Genic means made. So this is just man-made or human-made pollution. Anthropogenic pollution. So we've got three types of anthropogenic pollution. We have photochemical smog, industrial smog, and then particulates. Photochemical, if you break it down, you got your photo, you got your chemical. Sunlight plus chemicals gives you new nasty chemicals. In fact, that's it. Sunlight plus auto exhaust, new bad chemicals. Industrial smog. Coal burning releases sulfuric acid. releases nitric acid, releases mercury. So that's industrial smog. And then particulates are tiny bits, tiny particulate matter, tiny bits. For example, the smoke from fires. I've sent out a bunch of links about PM 2.5 pollution. Here's another article on why wildfire smoke is so bad for your lungs, talking about PM 2.5, which is particulate matter of 2.5 microns or smaller. So about a tenth the diameter of a human hair. That's how small. The particles are so small that they don't stay in your bloodstream. They actually come out of your bloodstream. They can cause lung damage. They can cause heart damage. So even though it may seem like there's no smoke, like today, the air looks clear. It doesn't smell like smoke, but looking at the air quality readings for this PM 2.5, it's really bad, around 150, very hazardous conditions. China has some of the worst air quality in the world. I think that's what happens when you let business pollute as much as they want. These are two pictures taken from the same location on different days. Same dealio. On the 19th, Beijing socked in with, that's not fog, that's air pollution. And then on the 22nd, the wind had shifted, blown it all someplace else. Of course, you can't get rid of things, right? Earth is a closed system for matter. This is New York in 1973, before the Clean Air Act. This is Texas, before the Clean Air Act. Smoke from burning car batteries, which would be sulfuric acid and lead. All kinds of incredibly hazardous chemicals we used to just dump into the atmosphere. This is the Cuyahoga River fire. The Cuyahoga River in Ohio caught on fire several times. It was one of the very dramatic events that led to the Clean Air Act and the Clean Water Act, both of those signed into law by President Nixon, who also oversaw the creation of the Environmental Protection Agency, the EPA. All of those came in under Nixon. So this is a diagram showing you different types of anthropogenic pollution. We've got those. These are all photochemical. I'll just say all of these we can just lump under photochemical smog, and that'll be good enough. Sunlight plus car exhaust gives us nitric acid, which throws off the pH balance of soil, can kill microorganisms in the soil, can kill plants if it's too acidic. Carbon monoxide is poisonous. It makes ozone. Oh, wait, that's good, right? No, that's bad. Ozone at the surface doesn't migrate up to the ozone layer to replace the missing ozone. Ozone at the surface causes lung damage. It causes crop damage. It wears out your tires. If you ever looked like at an old set of tires and they've got these cracks in the sidewalls and you wonder, how did that happen? The answer is ozone. What else? PAN, peroxycetyl nitrates. This is the brownish smog that you can actually see that hurts your lungs. And again, that's caused by exhaust from cars combining with ultraviolet radiation to make new chemicals that are also hazardous. So everything on this page, I'm just going to lump into photochemical smog. Industrial smog coming out of factories and power plants, and then particulates. So in the Central Valley, we have exceptionally bad air quality because the air is trapped in the valley, right? In fact, I think I forgot to mention that previously. The third factor that causes bad air quality in the valley is we're in a valley. So it just gets stuck. It doesn't make it up and over the mountains. So agriculture in the valley, plowing, for example, puts lots of tiny particulate matter into the atmosphere. So on this page, you got your industrial smog, which would be industrial chemicals that combine with sunlight or don't combine with sunlight, and then particulate matter. Yeah, so on this page, you've got industrial smog, which are chemicals released into the atmosphere from factories, carbon dioxide, sulfur dioxide, lead, mercury. They can cause brain damage. They can cause lung damage. And then we've got particulate matter, in this case, plowing from fields, but it would be wildfires, would be another source of particulate matter. So the Clean Air Act, signed into law in 1970, it has had a 22-to-1 cost savings ratio. For every $1 that companies have spent to reduce the pollution that they put into our air, we, the public, got $22 in benefits. So an enormously successful program. saving 100,000 deaths every year because the air quality is better, so people aren't dying prematurely. Massively fantastic program. And that's the end of the chapter. That's it for Chapter 1, Seasons and the Atmosphere. I hope you enjoyed it.